Hi everyone, welcome back to my channel. If you're new here, I'm Mukul. Today we are going to talk about something really cool in the world of AI and machine learning, and that is quantization in large language models, or LLMs as we know them. Don't worry if you haven't heard about these terms before. I'll explain everything in simple terms with a full analogy. So let's get started. Quantization is the method that is used to make large AI models smaller and faster. So imagine you have a big heavy suitcase full of clothes and you want to make it lighter without removing anything important from your suitcase. So quantization is like folding these clothes more neatly to save space and make the suitcase easier to carry. So technically, it means reducing the precision of the numbers. So inside a large language model, you have a neural network operating, which works with weights and activations. So it means reducing the precision of numbers, weights and activations that the model uses. So usually these numbers are stored at a very high precision, but we can make them simpler and smaller without losing much information. Right? So there is an optimization process that is going in within these models once they're returning back results. And you can tell the model that, hey, I don't want 100% a perfect answer. As long as it is 98% good, I'm good too. And this is where the quantization aspect of tuning comes into picture, where you reduce the size, but you still get close enough optimal performance from the models. So why do we need quantization? So there are three main reasons. One, smaller size. Two, faster performance. And then three, energy savings. So let's go into them one by one. So smaller size, AI models can be really big and they can take up a lot of space on computer. Quantization makes them smaller, so they fit better on devices like on your phone and tablet too, like the Phi 3 model that we have. So it's like making your suitcase lighter so you can carry it easily while you are on a trip. Faster performance. The smaller models can work faster. This means when you ask your phone to recognize your voice or translate a language, it can do it more quickly. Right? So, taking our suitcase analogy back, a lighter suitcase is easier to move around, so you can get to your destination faster, right? And then energy savings. A smaller, faster model normally uses less power than a big clunky model that we have. So it makes the energy impact lower on the systems that it is involved in. So, with the same analogy, we have carrying a lighter suitcase means you use less energy while you are carrying it. It makes your journey less tiring overall. So, there are two main ways to do quantization. One is a post training quantization, and second is a quantization aware training, right? So, what are these two things? Let's talk about them. So, post training quantization is like ironing your clothes after packing them to make them fit better. So, we train the AI model first and then we make it smaller, right? That's why it's called post training. And there are again two different methods involved over here. One is called static quantization and another is dynamic quantization. So in static quantization, we use a sample of data to help figure out how to make a model smaller. It's like packing with a plan, knowing what you'll need for your trip. And in dynamic quantization, we make the model smaller as it works. So it's kind of like adjusting on the go. So in our suitcase example, it is like rearranging your suitcase while you are traveling to make everything fit better, right? So you haven't planned things in advance, but you are rearranging while you are traveling to make things fit, nicely in your suitcase. And now the second way to do quantization is quantization aware training, right? The first one is after the training is done, and the second one is quantization aware training. So in quantization aware training, or QAT, in this method, we incorporate quantization into the training process itself. So the model is trained with quantization in mind, right? So simulating quantization errors and then taking action based on them during the training process itself, right? So that is what QAT means. So this helps the model learn to be robust to such errors, and often resulting in a better accuracy compared to a post-training quantization models, right? So it's more efficient in terms of models accuracy if you use the quantization aware training versus the post-training quantization, where we do the quantization process afterwards, right? So if you take the analogy of our suitcase again, the QAT, or quantization aware training, is like learning to pack your suitcase neatly from the start, right? So you know how to fold and arrange everything perfectly from the beginning, so it all fits well in your suitcase. All right. So how does the quantization process actually work? So let's see. There are 3 steps of quantization process. Step 1, scaling. 2 is clipping. And 3 is mapping. Scaling. So first, we figure out the range of values the model uses, right? So like the highest and the lowest points of the model. And think of it as measuring how much space each item in your suitcase takes up, right? So we determine the range of the weights and activations in the scaling step. Then step number 2 is clipping. So next we cut off any extreme values that are not really necessary, right? So it's like deciding not to pack items that you won't use, but they look cool, so you wanted to keep them. But if you're not going to use them, let's just cut them off and then not pack it to begin with. And this ensures that the data stays within a manageable range for you, right? So in other words, we clip values to a specified range to avoid extreme values that can affect the quantization process, right? So we clip them off. And the third step is mapping. So we convert these values to a simpler form. Like in our suitcase example, we use a packing list to organize everything efficiently, right? So in technical aspects, we map the floating point values to a lower precision format, like an 8-bit integer, using a scale factor, right? So we do not get into a more complex number, but we reduce the precision to a more simpler 8-bit integer number, right? From floating point to 8-bit integer is definitely reducing the complexity over here for us. So what are challenges of quantization? So it sounds cool, it sounds good, but there is always a catch in every process, right? So quantization also comes with some challenges. Number 1 is loss of accuracy, right? So making the model smaller can sometimes make it less accurate. Like if you fold clothes too tightly, they are going to get wrinkled. Right? So in technical words, reducing the precision of the model can lead to a loss in accuracy. Second, hardware needs. So not all computers or devices can handle these smaller models efficiently. So it's like needing the right kind of suitcase for your neatly packed clothes. In technical aspects, efficient quantization requires hardware that supports low precision arithmetic, right? The third is fine tuning. So, getting the model to work well after quantization can be tricky. So, it's like making sure everything still fits perfectly after you have changed the orientation, compacted it correctly, and now you're making sure that everything still fits, right? So in technical aspects, finding the right calibration parameters to minimize the accuracy loss can be complex. Now, these are the high level ideas of what quantization is. And in summary, quantization is a technique to make large language models smaller, faster, and more efficient. It's like packing a suitcase in a smarter way, like how I've been defining it on the go. Whether you are working with AI on a big server or on a small device, quantization can make a big difference. So there are a few papers that I would highly recommend if you want to go and dig deeper into quantization. This was the very first paper, 8-bit matrix multiplication for transformers at scale. And I really enjoyed reading this paper. Basically, it was one of the first papers that outlined some of the challenges of deploying large language models and suggested quantization as a way to reduce the model size. And their quantization specifications were able to quantize models up to int 8, right? So that's why they called it LM int 8 function. And their int 8 precision changed the model accuracy, which they introduced that the concept of perplexity scores. Very little change in the perplexity scores, right? So there were again issues with everything. So even though they were able to reduce the model size, their quantization spec had an overhead, which caused an increase in the model latency. So you can actually use this technique of quantization in Hugging Face to quantize a model too. And this is a very interesting paper that I think you guys may like to read if you want to see a couple more details of quantization. The second one is GPTQ paper. And this paper was able to take a step even farther and quantize LLMs to as low as 3-bit precision. They found that the model size gets larger, the precision loss due to quantization has a negligible effect on the quality of the model, right? So this is an interesting result. And this is again one of the papers that I would recommend if you'd like to dig deeper and take a look. You can do that. The third paper that I think is an interesting paper is RPTQ, reorder based post training quantization for large language models. Right. So one of the reasons for drop in quality with quantization is the loss in precision of the weights. And this method tried to solve this loss in precision by clustering similar weights and activations and then quantizing it after, right? So this allowed them to quantize both activations and weights to 3 bits. And this is a very interesting paper, and I would recommend if you are interested in learning about quantization, take a look at this too. And last but not the least, there's an amazing project that everyone is talking about, and that this is our llama.cpp. And I've been following this project closely. Their int4 quantization spec is really simple, and you should take a look over here too. They take a group of 32 consecutive weights and assign a scaling factor, and they do a 0 offsets over here, and then you can attain better performance with the way how they have been using the 4-bit integer quantization over here, right? So they can quantize the 6 billion parameter GPT model with a size of about 11 gigs to 3.5 gigs, I think is what they had, or whatever. There it is. So GPT-J model, 11 gigs to 3.5 gigs, which is huge. So this is all I have for today. Please let me know how you like today's video, and I will see you in the next one. Thank you.